Because if you watch the YouTube, the one that's on the YouTube right now, was recorded on a tablet of me writing on the tablet on the notes. But that's also like the first time I've done that, so my tablet handwriting is worse yet than my normal penmanship. And there were a few just like mistakes made, so we'll see if I make a different set of mistakes this time. So let's let's think about the goal for the rest of the class. I think the last big theorem goal that I want is the proof of the existence of solutions to initial value problems. So, what is an initial value problem? An initial value problem is a problem that takes the form the derivative of a function is equal to something that depends on the values the function takes and the independent variable x, and specifies some initial value. So those are the types of problems that you solve a little bit in Calc 2 and more so in the differential equations class. Have people here have taken the diffeq class? Did you take the diffeq part 2 class? Oh, okay, so does Chris prove this theorem using some technique? Okay, good, because we will. So you should think of these as just being like, yeah, the function big F had better be continuous. Of course it is if we plan on using analysis-driven techniques. The initial value had better be in some domain on which the function is continuous. The absolute value of big F should stay bounded. I mean, all those conditions get technical, but the point is that that initial value problem, so there's some function little f, which satisfies these conditions, at least on some very small interval containing the initial value x0. That's all. But let's think about what you would need to do to solve that. So in things like abstract algebra, you introduce groups and rings and fields, and those model the places where you expect to be able to solve algebraic equations. But a differential equation doesn't necessarily need to have any algebraic structure you can really take advantage of. A linear differential equation might, but there's nothing here specifying anything about linearity. So you need to look for some space where the solution will live. And so the space is going to be like the set of all functions, but there's no structure there. You need to specify something about the set of all functions that you can take advantage of. And you'll remember, so in analysis 1, we solved some equations by proving things like the intermediate value theorem. And what was one way that we solved the intermediate value theorem? Well, one way to do it is to set up a sequence of numbers, show that that sequence of numbers has to converge, and show that that sequence of numbers comes closer and closer to solving some equation. That's one way of solving these things. So here's a way to try to approach this sort of thing. Construct a sequence of functions, show that that sequence of functions converges, whatever that means, and then show that the sequence of functions comes closer and closer to satisfying that equation. And then maybe if you set it all up correctly, you would take the limit of everything in sight and say, oh, the limit of this sequence of functions is the thing we want. So we need to set up some stuff. We need to be able to talk about taking limits of sequences of functions. And you'll remember from Calc 1, there were two types of limits of sequences of functions we talked about. Remember what they were? There's the pointwise limit and the uniform limit. We'll generalize those further, saying, well, if we can come up with a sense of what it means to measure distance, that's all you need to talk about the limit of a sequence. So let's establish what we mean by distance. Well, let's do it totally in the abstract, same as you would talk about a group in the abstract. So a metric space is a set together with some function, a distance function, which you should measure the distance between two elements of x. So the metric, the distance function is going to take, the domain is going to be pairs of inputs. and it will produce a real number. I'll call that a distance function, or I'll call it a metric. And a metric, there should be a space there, and maybe I'll make both of those. Those two should be the same article. A metric should satisfy the following conditions. If you take any 3 things in the domain, the distance from y to x should be the same as the distance from x to y. So distance should be symmetric. The distance should never actually be negative. The distance between 2 points shouldn't be negative. Moreover, the distance between 2 points is 0 if and only if those 2 points are the same points. And finally, the triangle inequality should be satisfied. If you want to measure the distance from x to z, well, one way of getting it bound is by finding some other point y, measuring the distance from x to y, adding that to the distance from y to z. The straight line distance from x to z had better be small. So that's why it's called the triangle inequality. It's that picture. Of course, this distance doesn't have to do anything with straight lines. So here's the content of today. So we have this abstract object called a metric space. We should probably actually verify that some things are metric spaces. So let's just list some. Here's the prototypical example. You want to, metric spaces are supposed to be places where you can do analysis. And here's one place where we can do real analysis, the real line. So here's the prototypical example. The real line is a metric space where you measure distance by taking the absolute value of the difference. That seems reasonable, right? Metric spaces are, however, much more flexible. And just in order to illustrate that, here is a silly example. The discrete metric, let x be an exact, and the distance function be given by, well, the distance between any 2 points, well, it needs to be 0 if they're the same point. That's one of the axioms. And let's just set the distance between any other 2 points to be 1. And that's called the discrete metric because nothing is close to anything else. Everything is discretely spaced out. And so if you like, you can think of that as taking the set you want to study and just hitting it into a hammer so you've shattered it into a bunch of little pieces, and none of the pieces know where any of the other pieces are. So that's a good example to go through, but the discrete metric in general doesn't tell you much. Can't be used to solve problems. And finally, the last example that I want to do is the distance function that we already know should be imposed on Rn. If I give you 2 points in Rn, then you measure the distance via the distance formula. So there's the formula for distance in Rn. We'll prove that that's a metric. And that's all we'll do today. And we'll do these things in however much detail people want to see. Let's start by showing the distance function given by absolute value of the difference is a metric. So we need to check 4 conditions: symmetry, non-negativity, positivity, and triangle inequality. So let's check for symmetry. Why should the distance from x to y be the same as the distance from y to x for this distance function?
Because you can pull out an absolute value of -1 times the absolute value of x minus y and make it effectively the same.
Yeah. Great. But if you want to measure the distance from, well, I think you started with the y up front, distance from y to x. That's the absolute value of y minus x. But that's the same thing as -1 times x minus y. Yeah, so it satisfies the symmetry condition. And you'll notice that, if your answer was just what I wrote, that would definitely not be complete because you should probably quantify some things. Let's check why it's non-negative. Why should this distance function be non-negative?
Absolute value is non-negative.
By properties that we've proven about absolute value in analysis 1. And I know that we proved that in analysis 1 because you all took analysis 1 for me. the distance from x to y is equal to the absolute value of x minus y is bigger than or equal to 0 by properties of absolute value. Nice. Positivity. So my positivity is an if and only if condition. It's distance from x to y is equal to 0 if and only if x is equal to y. So you prove an if and only if by proving two things. Let's prove two things. Suppose that x is equal to y, then why should the distance from x to y be 0?
Because the absolute value of x minus x is 0.
Because the absolute value of x minus x, which is the absolute value of 0, is 0. Yeah. Great. Conversely, if x is not equal to y, then why should the absolute value of, why should the distance from x to y be strictly positive? So we can do the cop-out, it's a property of absolute value proof, or we can do the actual case-wise proof. Or if people want to see some cases. Let's see some cases. So walking over the real line, so we know everything that we know about the real line. If x is not equal to y, then the trichotomy law for the real number says one of two things happens. Either x is bigger than y or x is less than y. Yeah, right? So let's see, by trichotomy, either x is bigger than y or x is less than y. Let's assume x is bigger than y. Right, distance is symmetric. So there's definitely a without loss of generality. You could switch the x and y and always have the first one first. Let's try to compute the distance from x to y. So that'll be the absolute value of x minus y. Okay. Is x minus y positive or negative? Positive. So what's the absolute value of x minus y?
X minus y.
X minus y. So the distance from x to y, right now it's x minus y. Is x minus y bigger than 0? Because x is bigger than y. Nice. That's all we needed. The triangle inequality, in general, this will be the most involved of the results to check. And it's no different here. If you recall when we proved all these properties in Real 1 about the absolute value function, the triangle inequality for absolute value was the hardest thing to prove. Let's prove it though. So consider any x, y, and z in R. We want to show the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z. And I'll break it up into cases. I guess first things first, we may as well assume that x is less than z. If they were in the opposite order, you could use symmetry to switch everything around. And there are now three cases. Either y comes before x, y comes between x and z, or y comes after z. In fact, multiple of these cases might simultaneously be true. But that doesn't matter when you're doing a case-wise thing. Having two cases apply at the same time is just fine. So let's try to prove these, and let's do it by let's see, in the version, this is where some of the errors happened in the notes if you just watch the ones that are already posted. But let's try to prove this by doing some scratch work on the bottom first, because we know what inequality we want to show. So let's break it up into each of these cases. Let's suppose that y is less than or equal to x, and we assume that x is less than or equal to z. So in this case, we want to show here's the thing we want to show. Let's just expand everything out. What's the definition of the distance from x to z?
Absolute value x minus z.
So I want to show this is less than or equal to and I know that on the one hand you can say, well, that's exactly the triangle inequality we proved in wheel 1. But let's just try to expand everything out. Is x bigger than z or is z bigger than x?
Z bigger than x.
So what is the absolute value of x minus z?
Z minus x.
Maybe I'll put a question mark there because it's what I want to prove, not something that I get to know. What's the absolute value of x minus y?
X minus y.
Because x is bigger than y. What's the absolute value of y minus z?
Z minus y.
So apparently we want to show this. So let's just try to convince ourselves that that's true. And then we'll have our argument, we'll just run this set of moves backwards. So what would you want to do to simplify this to something that's obviously true? What would you want to do to simplify that?
Combined terms cancel the z's. Move to the x over.
Is that obviously true?
Yeah, when x is bigger than y.
So now we have our proof. Let's just write it down these same steps, but backwards. So, because x is bigger or equal to y, 2x minus 2y is bigger or equal to 0. Alright, to go from here to there, there's just some like adding stuff to both sides. So, by doing some algebra, what do we get? I see that z minus x is less than or equal to x minus y plus z minus y. And let's even put some helpful parentheses. There's a plus sign between those. All right. Cool. So now the next step was translate everything into absolute values. So why was z minus x the same thing as absolute value of x minus z?
Z is greater than or equal to x.
Why was this the same as that? Because x was...
That's bigger than or equal to y.
So, because y is less than or equal to x is less than or equal to z, we see z minus x equals absolute value of x minus z equals the distance from x to z. Y minus x is equal to the absolute value of y minus x is equal to the distance from y to x, and z minus y is equal to absolute value Thus, the distance, by making substitutions from x to z, is less than or equal to the distance from x to y plus the distance from y to z. That seems pretty okay to move on? I think the other cases will be pretty similar. In fact, do you want to go through the remaining ones? Is there demand to go through the remaining two? Okay. Maybe I'll say that this one is different in that in this case you actually get equality instead of inequality. But inequality is okay. Less than or equal to is satisfied when equality is satisfied. Nice. So now let's do an example that feels a little bit more abstract, because it is more abstract. Let's take the discrete metric on an arbitrary set. So I don't know anything about this set. Let's show that it satisfies all of the conditions to be a metric space. So there are 4 conditions we need: symmetry, non-negativity, positivity. Sometimes those two are combined into a single item. And finally, the triangle inequality. So let's do it. Consider any x and y in X. Why should the distance from x to y be the same as the distance from y to x? Well, how about if we just try to compute both sides using like a case-wise argument? All right, there are 2 cases. Either x and y are the same or they're not the same. There's no inequality we can use. Well, let's see. Well, if x is equal to y, then what's the distance from x to y?
0.
What's the distance from y to x?
0.
Would it be fair to just say, like, trivially, like, d of x is equal to d of x? Because, like, they're the same. Just, like,
Yeah.
Swapping. Okay. Just wanted to make sure.
Yeah, that's fair. You could write them both as d of x comma x. No, that's maybe a better way than what I did. What if they're different?
d of x y equals 1 equals d of y x.
I don't know.
Cool. Non-negativity. Explain to me why the distance is always non-negative.
By the definition of the function, the smallest degree is 0.
Yeah, it can only take 2 values, right? The only values the thing takes by its very definition is 0 and 1. Neither of those are negative. Positivity. Considering x and y in R, suppose x is equal to y, tell me why the distance is 0.
Have a definition.
Suppose x is not equal to y, why is the distance positive?
Because it's 1.
Because it's 1.
1 positive.
Yes. So if you recall from the axioms of the real numbers, the order axiom of the real numbers stipulated that there was a subset of the real numbers called the positive numbers, and we proved that 1 had to be in that set.
Oh, yeah.
So yes, 1 is indeed positive. The triangle inequality. We need to prove that the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z. I thought that there are only 3 possible cases. Either they're all the same, or y is different from at least one of x and z. Let's just take a moment and convince ourselves that these are actually all of the cases. Indeed, let's suppose that neither of those held. So if you did not have x is not equal to y, then x would have to be equal to y. If you did not have y is not equal to z, then y would have to be equal to z. Are you now in the Haas case? So sometimes multiple of those cases might hold, but again, that's fine. So let's do it. Let's suppose that x is equal to y is equal to z. Let's figure out why the distance from x to z is less than or equal to the distance from y to x plus the distance from y to z in this case.
From 0 less than or equal to 0 plus 0 is true.
Well, the distance from x to z is equal to 0, is less than or equal to 0 plus 0, is equal to the distance from x to y plus the distance from y to z. Great. Presumably the other two cases will be pretty similar to each other. So let's try to do just one of those two cases. Let's suppose x is not equal to y. And now we'll try to explain why the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z. And let's write down the one thing we do know. Under these conditions, what's the distance from x to y? 1. So no matter what can you tell me about the distance from x to y plus the distance from y to z? What could that number possibly be?
At least 1.
At least 1. It might be 2. Now, on the other hand, let's look at the other side, the distance from x to z. What values could that possibly be?
0 or 1.
Equals 0 or 1. So, either way, do we get the inequality we need? Nice. And what do you think? Is that last case going to be the same thing again? Just some of the symbols will be permuted? Cool. So those were some reasonably light examples of proving a thing is a metric space. And a thing to notice in each of these examples, generally speaking, the thing that's the hardest to prove about a thing being a metric space is the triangle inequality. Sometimes it's hard to prove that a metric is actually positive. Depending on how you define it, you might have the unfortunate situation that you can't necessarily prove that your metric detects two things being equal. In that case, you don't call it a metric, but there is a thing called a pseudometric. Maybe it would be cool to do some examples of pseudometrics. So, final example. Let's prove that Rn with the standard distance function, distance 1 is actually a metric space. You'll notice that in the notes as handed out, there's a square root missing. So this theorem will use heavily an important inequality in analysis, an important inequality called Schwarz's inequality, which says that if you have any sequences of numbers called u and v, finite sequences, so I guess that is n tuples. You can prove an infinite version of this, but I'll only need the finite version of this. For now, if you add up the product of u and v, of all the u's and v's, multiplied together, that's less than or equal to the sum of the squares of all of the u's times the sum of the squares of all of the v's with the square root over. There is a proof, in fact, it's outlined on the last page of the note packet you have in front of you, of this lemma. And I mean, one strategy is inducting on that natural number n. If you write down what both sides are when n is equal to 1, you see that it's like just true. But let's not worry about the proof of it. Let's use that and prove that the standard distance function is actually a metric. So, maybe we'll even just say ideas. Then using that distance function, why should that be symmetric? Why should I be able to switch the rule of x and y?
X minus y squared is the same as y minus x squared.
Yeah. So you check that each term of the sum has the property that you can interchange the xi and the yi. There you go. Do you want me? Should I write anything? Okay. Why should it be non-negative?
Each term has to be greater than or equal to 0. So the only way for it to.
Just worry about non-negative.
Oh, yeah.
You're trying.
Each term has to be greater than or equal to 0, so it all has to be greater than 0 when you add it up.
Yeah.
Greater than or equal.
You add up a bunch of non-negative things. Well, a square is always non-negative. This is real analysis, not complex analysis. You add up a bunch of non-negative things. You get something non-negative. You take the square root of a non-negative thing. You get a non-negative thing. Should I write any words, or is that? Maybe I'll just stall for a second and let you guys write the words. Positivity. Consider any x and y in Rn. If x is equal to y, then tell me why the distance from x to y should be 0.
Xi minus yi equals 0 for all I.
Cool. So that means that, well, 0 squared is 0. Sum of a bunch of zeros is 0. Square root of 0 is 0. Continuing down, let's suppose that x is not equal to y, and prove that the distance from x to y is strictly positive. And maybe this one I'll actually write something down. Because what does it mean for one n-tuple to not be the same as the other n-tuple? Well, to understand that, think about what it means for one n-tuple to be the same as another n-tuple. Two things are equal if each of their entries are equal. So if x isn't equal to y, then they differ at some point. So there is some j with xj not equal to yj. So let's try to expand out from that. So if xj is not equal to yj, then what can you tell me about xj minus yj squared?
Greater than 0.
It's greater than 0. So, how does this differ from the thing in the sum? The thing in the sum just contains a bunch of more things, and all of those things are non-negative. So the sum from of xi minus yi's squared from I equal 1 up to n is bigger than or equal to xj minus yj squared, since bigger than 0. This is a sum of non-negative things. Well, then what I've basically done, right? If I take the square root of something that's positive, do I get something that's positive? Thus, or maybe then, the square root of the sum of all the xi minus yi's squared is strictly bigger than 0, so the distance from x to y is strictly bigger than 0. So, right, that took some words, but like, ultimately the proof was pretty easy for that step. The triangle inequality. in general, is the harder of the ones to do. Oh, so maybe I should like pause for a second and say, how many people have already looked at the PDF that is the homework problems assigned for this note packet? So you'll notice that one of the items was the proof the Schwartz inequality. The other two will prove the two other things are metrics on our end. The L1 metric and the L infinity metric. So that maybe tells you that there are probably there are a bunch of numbers between 1 and infinity, and 2 is just one of them. In fact, there's a whole bunch of metrics there called the LP metrics. One for every number between 1 and infinity, including 1 and infinity. You can define the LP metric when P is like a half, but it won't be a metric. So, with that out of the way, let's try to prove the triangle inequality. And here's going to be the strategy. I'll try to show that the distance from x to z squared is less than or equal to the distance from x to y plus the distance from y to z squared. That's what I'll try to do. So that's how this thing will be rock shot. So I guess the two things we could do, we could just jump straight into giving the proof. Yeah, let's actually just do that. Let's jump right into the proof. So let's just do this. Let's expand out the distance formula. So what's the distance from x to z? What is that squaring?
The sum I equals 1 to n of xi minus zi squared.
Fair enough. And I suggest that what I'm going to wind up doing is adding and subtracting a bunch of yi's. And there are always two things you should wonder about, like, is this actually something that you can do, and is it something that you should do? Let's not worry about the second yet. Let's just check that it's something you can do. You can always add and subtract a single number. In fact, you can add and subtract a single number n times, and you still get equality. I'm going to stop indexing my sums. They're all indexed from 1 up to n. So all of this will be squared, and then I'll add some helpful parentheses around those two pieces. And you'll see that, like, up there, I want to get the distance from x to y plus the distance from y to z squared. Do you see in that sum that there's something that looks an awful lot like the distance from x to y showing up already? Yeah, if I just had the square over this term and the square over that term, I would have the distance from x to y squared and the distance from y to z squared. But that's not how squares work, is it? One must FOIL.
We're working over a field of characteristic 2.
Are we walking over a field of characteristic 2?
I don't think so.
Is R a field of characteristic 2?
It's a field of characteristic 0, and 2 is a divisor of 0. That's how that works.
So you FOIL this out, and you see that you will get the sum of a bunch of things that look like xi minus yi squared plus, and maybe I'll FOIL in the right order, plus 2 times xi minus yi times yi minus zi plus yi minus zi squared. Cool. Do you now actually see, if you broke that into 3 pieces, would 2 of the pieces just be distance formulas squared? Yeah. Break it up into 3 pieces, you see the sum of all the xi minus yi's squared. Maybe for emphasis, all of that is being summed up right now. Let's draw some big parentheses. Plus the sum of all of the yi minus zi squareds plus 2 times the sum of all of the xi minus yi's times yi minus zi's. And now I see some distance formulas. Maybe you guys already wrote the distance formula bits to in. That's the distance from x to y squared plus the distance from y to z squared plus 2 times the sum of a bunch of things that look like xi minus yi times yi minus zi. So I'm going to go ahead and on the board rewrite Schwarz's inequality because we're about to make use of it. So let's write down Schwarz's inequality. The Schwarz inequality says, write it somewhere where everyone can see. If you add a bunch of UIVI's, that is less than or equal to the square root of the sum of all of the UI's squared times the sum of all of the VI's squared. So I have that written down up there. Let's look at the piece that we are actually interested in. Like, that's the piece that looks complicated. So let's see what the Schwarz inequality says about that. Is that a product of a bunch of is that a product of a bunch of one thing times a bunch of another thing?
Yeah.
Yeah. So let's use the Schwarz inequality, where this is my u, and that will be v. So, applying the Schwarz inequality, that tells me that this whole sum is less than or equal to the distance from x to y squared plus the distance from y to z squared plus the 2 will come along for the ride. And now let's just copy down what the Schwarz inequality says. It will be the square root of, I'll figure out how big the square root needs to be once I've written it down, a sum of a bunch of xi minus yi squareds times the sum of a bunch of yi minus zi's squared, finish the square root. Hey, you see some more copies of the distance formula sitting in there now? Yeah. There's distance from x to y squared, but it's under a square root, so it's really just the distance from x to y. There's a distance from y to z squared, but it's under a square root, so it's really just the distance from y to z. So the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z plus 2 times the distance from x to y times the distance from y to z. And so right there are 2 different levels of following a proof. Has each step actually followed from the step before it? And now do you so given the goal that's written up at the very top of the page, so beyond the screen, is it clear how to get to there from here? So there's the proof that the things that we did were things that we should have done, because now we see how to get to our destination.
Where did these squares go? Yeah.
Yeah. Let's look at this bit. So what we see there is the square root of the distance from x to y squared times the distance from y to z squared. Do you see a perfect square underneath that square root? So, the squares and square roots will just cancel.
Not there.
Oh.
Earlier.
Oh.
In that line.
Oh, yeah,
Okay.
yeah, absolutely those should have squares on them. you were just nodding along means that like
I had it.
you had them there.
Yeah. I didn't even notice.
So I know it's back on, right? Thing squared plus 3, thing squared plus 2 times first thing times second thing. That's just the sum of the things squared. There are rare occasions that I give myself more space than is needed in these lines. So I've just proven that the distance from xy is less than or equal to, the distance from xy squared is less than or equal to the distance from, you see what I've proven, you see what's. So a thing squared is less than another thing squared. Are both of those things non-negative?
Yeah.
Squaring is monotone over non-negative things. So I can erase the squares and resolve the inequality. So that means the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z. So the triangle inequality is indeed satisfied, and the L2 metric is indeed a metric. Did that go okay? Good. So one of the things that is homework is the proof of the Schwartz inequality. And an argument here is outlined using induction on the number of variables. And in order to see that induction is maybe a decent way to do it, let's just write down what this inequality becomes when n is equal to 1. See, when n is equal to 1, you just get u1 times v1 on the left-hand side. What do you get on the right-hand side? You get the square root of u1 squared times v1 squared. Is that inequality true? Oh, and let's even point this out. So we actually use, it's more common to use the Schwartz inequality with the square root there, but it's easier to prove the Schwartz inequality where you move the square root to the other side as a square. So what we'll actually prove is that, which is the same, right? And in fact now, yeah, those are actually equal, right? So the base case should be easy. The inductive step will take a little bit of work, but it won't take that much work. Because you can express the sum of n plus one thing with the sum of n things plus another thing. So there's a setup there to use induction. Nice. So I'm at time, so I should stop. Maybe I'll point out that the version of, I was concerned for a little bit, because the version of the notes that I went through on the tablet turned out to be like 56 minutes long. That's why I was encouraging you guys to let me skip some of the steps.